These notes are on irrational and complex roots and intercepts. So we've already talked about the 5 different methods I can use in order to solve a quadratic. And I've mentioned in that previous video that I generally prefer completing the square. But as long as the roots are integers, any of the methods work. Well, in this case, our roots aren't integers. I can't factor x squared plus 4x plus 6. And so I'm going to go back to my favorite method, which is the completing the square. So I have x squared plus 4x, and I'm going to move my 6 over to the right-hand side. Then I'm going to complete my square, so I'm going to add 4 and add 4 in order to keep my equation the same. I now have a perfect square trinomial, which I can rewrite as a perfect square binomial. And now I have the square root of x plus 2 quantity squared equals the square root of negative 2. And now I'm in trouble. Remember, we can't take the square roots of negative numbers. There's no number that times itself equals negative 2. So mathematicians, after many years, decided, you know what, forget this. We need to decide that there's a method for this. And part of the reason why they did this is because if I go to my calculator and I graph this function, x squared plus 4x plus 6, I get a graph. I get a graph of a parabola. That is still a parabola even though it doesn't hit the x-axis. So we needed some way to represent these roots when they're not intercepts, when they don't hit the x-axis. So the intercepts we talk about as when the solution to a quadratic crosses the x-axis, where roots are going to be any solution. And so mathematicians decided, okay, so we need some way of talking about solutions that don't hit the x-axis. So they came up with this concept of what the square root of a negative number means. So they said that the square root of any negative number, they were going to rewrite that as the square root of negative 1 times the number, which is the square root of negative 1 times the square root of the number. And then they said, you know what though? Every time we do this, we don't want to rewrite the square root of negative 1. That's too much writing for us. We want a simpler way. So now we're going to replace that number with the letter I. So the square root of any negative number can be rewritten as I times the square root of the number. So when I continue working on this problem, so at this point I say a big, oh no. And mathematicians say, well, here's our fix. So now I can continue the problem. Remember when I'm taking the square root of a perfect square, and one of part of the perfect square is a variable, I need to indicate that it has to be a positive answer in the end. So I have the absolute value of x plus 2. And now I can use my fix. I'm going to rewrite this as I times the square root of 2. So now I follow the exact same methods that I've been using. It's just that I have a letter which representing a very particular special kind of number in the mix. So I have x plus 2 equals positive I square root of 2, or x plus 2 equals negative I square root of 2. So 2 possibilities. Now, when I want to finishing this, I'm going to want to, if I'm finding the solutions, the roots, the intercepts, in this case, not intercepts, roots, I still want to get down to where I have x alone. So I have x equals negative 2 plus I root 2, or x equals negative 2 minus I root 2. So I now have, we're going to indicate that these are our solutions. We can write these as x-intercepts, so negative 2 plus I, we can write these in terms of roots, and we write them in terms of roots as if they're x-intercepts, but they're not. So I can write them in terms of roots, so negative 2 plus I root 2, comma 0, and negative 2 minus I root 2, comma 0. We can also write this in factored form. So this is a little side note. So either I can write my answers as solutions or as roots. Your teacher may have preferences, so you'll want to talk to them about which method they prefer. But let's also talk about this in terms of factored form. So remember, in factored form, I'm actually going from the place where I have that I'm normally solving for x, but in factored form, I want two pieces that equal 0. Well, how do I get this piece to equal 0? I subtract I root 2 on both sides. How do I get this piece to equal 0? I add I root 2 to both sides. Now I have two things that equal 0. And we know that if I'm looking for the roots, the intercepts, the solutions, that I want an equation where those two things that could possibly equal 0 are being multiplied. And when I multiply them, they equal 0. So I now have the quadratic function that I started with written in factored form, even though we initially started this problem by saying that it wasn't factorable. So just because it's not factorable in the initial part of the problem doesn't mean that I can't work it out and write it in factored form. It's just going to look different than what we've looked at when we've talked about factoring quadratics. We've talked about factoring them only when we have integer solutions, roots, intercepts. Let's look at a second example. So, again, this doesn't factor, so I'm going to use, I'm going to first graph it, just get a sense of where the function sits. So y equals x squared plus 4x plus 2. I graph it. Look at that. In this case, it does cross the x-axis. So these are intercepts. Also roots. However, I can see both because I can't factor this and I can see on my graph, I'm not crossing at an integer intercept, an integer root, an integer solution. So I can't actually finish using my calculator at this point because I'm going to get an approximate value. So I'm going to go back to my completing the square method. So I have x squared plus 4x equals negative 2. Complete my square, add 4 to both sides. I get x plus 2 quantity squared equals 2. Square root both sides. Absolute value. So then x plus 2 equals positive root 2, or x plus 2 equals negative root 2. And so now I have lots of, I can talk about this. I can write it as first my solution. So x equals negative 2 plus root 2, or x equals negative 2 minus root 2. So there's the place where I have the solution. I can write it as intercepts. So negative 2 plus root 2 comma 0, and negative 2 minus root 2 comma 0. So there's my intercept, which are also roots, but not all roots are intercepts. And then I can also write it in factored form. So I go back up to this step. So I have x plus 2 equals the square root of 2, or x plus 2 equals negative square root of 2. And I want to get each of them to equal 0, so that when I multiply them together, that equals 0. So I have x plus 2 minus root 2 equals 0, and x plus 2 plus root 2 equals 0. So when I multiply them together, they're going to equal 0. Which means I now have my original equation written in factored form. So again, even though we could not factor the original problem, doesn't mean I can't write it in factored form. It simply means that I cannot factor it because the factors are not integers. And I can't, starting to list all of the factors of 2 when the factors themselves aren't integers becomes an impossible task at that point, because then it's, infinite number of numbers multiplied together equal 2. It's a matter of finding the exact right non-integer ones that do that. And so the easiest way to get factored form in that case is to complete the square and then sort of work backwards from the place where we start getting our solution to rewrite it in that factored form. The last thing I want to talk about with these notes is the fundamental theorem of algebra. So the fundamental theorem of algebra says we have polynomials, and polynomials can be written in this form, where we have various different coefficients in front of our x's, and our x powers, the powers of our x's, can start at some high number and descend all the way until we have x to the 0, which is 1. And it turns out that mathematicians discovered that when we have an nth degree polynomial, meaning the highest power is n, it means that we'll have n roots. So if I have f of x equals ... x to the 4th ... that means I will have 4 roots. And if I have g to the x equals anything x to the 10th plus ... I will have 10 roots. With the caveat being that 4 is the highest power, or 10 is the highest power.